The original problem, known as the Byzantine generals problem, was introduced in a computer science paper published in 1982. The paper discussed the challenge of maintaining reliable computer systems in the presence of faulty components that may send conflicting information. This issue becomes even more critical in decentralized computer networks. To illustrate the problem, imagine a scenario where the Byzantine army surrounds an enemy city. The army consists of multiple units, each commanded by a general who needs to devise a coordinated plan of action. However, the generals are physically separated and can only communicate through messages. Furthermore, some of the generals may be traitors, potentially sending misleading messages to disrupt the coordinated plan. To overcome this conundrum, the Byzantine army requires an algorithm that can achieve coordinated action, ensuring that loyal generals follow it while excluding the traitors. This solution is known as the Byzantine fault tolerance algorithm. Over the years, various theoretical solutions involving game theory and mathematics have been proposed. The practical implementation of the Byzantine fault tolerance algorithm was first seen in Bitcoin's proof-of-work consensus mechanism. In the context of cryptocurrency mining, the generals refer to the nodes on the Bitcoin network, commonly known as miners. A network node serves as a connection point that can send, receive, store, and create data within the network. In the Byzantine fault tolerance algorithm, mining nodes assume that no one else on the network can be trusted. Proof of work ensures network consensus even in the presence of non-compliant nodes, allowing coordinated action to be achieved. In Bitcoin, mining involves participants performing proof-of-work calculations to generate new coins as a reward. These calculations require extensive computational power and aim to solve cryptographic hash puzzles, which enable the network to function and facilitate the exchange of transaction messages. Miners collect and verify new transaction data, ensuring various criteria are met. Verified transactions are then aggregated into transaction pools, waiting to be included in a new block. Miners compete to be the first to create a valid block by arranging the verified transactions and constructing the block header. The block header contains a summary of the transaction data, a reference to the previous block, a timestamp, and a valid proof of work. The summaries of the block contents are generated using hash functions, which process the data to produce a unique identification code or digital fingerprint for the block. Cryptographic hash functions, such as SHA-256, Secure Hash Algorithm 256-bit, play a crucial role in proof of work. These functions can transform any data, regardless of size, into a fixed-length string of characters, serving as a unique identifier. However, cryptographic hash functions are one-way functions, meaning it is impossible to reverse engineer the original input data from the output. To find an unknown input, one must attempt different values systematically, essentially employing a brute force approach to solve the cryptographic puzzle. This process constitutes the work required in proof of work, involving iterative computations by computers to find a solution.